Mathematical models relate to extreme values of function. Before we learn about mathematical models relate to extreme values of function, let's learn about the second derivative first. A derivative basically gives you the slope of a function at any point. The second derivative is the derivative of a function. So, find the derivative of a function, then take the derivative of that. A derivative is often shown like a little tick mark. We can read it f accent x. The second derivative is shown with two tick marks like this. We can read it f double accent x. Example: fx equals to x cubed. Its derivative is f accent x equals to 3x squared. The derivative of 3x squared is 6x. So, the second derivative of fx is f double accent x equals to 6x. A derivative can also be shown as dy per dx. And the second derivative shown as d squared y per dx squared. Example: the previous example could be written like this. Y equals to 3 cubed dy per dx equals to 3x squared. D squared y per dx squared equals to 6x. Stationary points. The second derivative can be used as an easier way of determining the nature of stationary points, whether they are maximum point, minimum points, or points of inflection. A stationary point on a curve occurs when dy per dx equals to 0. Once you have established where there is a stationary point, the type of stationary point, maximum, minimum, or point of inflection, can be determined using the second derivative. First, if d squared y per dx squared is positive, then it is a minimum point. Second, if d squared y per dx squared is negative, then it is a maximum point. Third, if d squared y per dx squared equals to 0, then it could be a maximum, minimum, or point of inflection. Fourth, if d squared y per dx squared equals to 0, you must test the values of dy per dx either side of the stationary point, as before in the stationary point section.
Example 1. Determine the type of stationary point from fx equal to 4x cubed minus 18x squared plus 15x minus 20 by using the second derivative test. Answer: Step 1. Find the second derivative from that function. Fx equal to 4x cubed minus 18x squared plus 15x minus 20. First derivative x equal to 12x squared minus 36x plus 15. We can simplify to be 3 multiplying 4x squared minus 12x plus 15, and factor equal to 3 multiplying 2x minus 1 and 2x plus 5. Second derivative x equal to 24x minus 36. Step 2. Find the stationary point by using factorization from first derivative. First derivative x equal to 0. 12x squared minus 36x plus 15 equal to 0. The factorization 3 multiplying 2x minus 1, 2x plus 5 equal to 0. 2x minus 1 equal to 0, or 2x minus 5 equal to 0. X equal to a half, or x equal to 5 per 2 equal to 2 a half. Step 3. Find the value of second derivative by using stationary point for x equal to a half. Second derivative x equal to 24x minus 36 for x equal to a half. So, second derivative for x to equal to a half equal to 24 multiplying a half minus 36 equal to 12 minus 36 equal to minus 24. Function f(x) equal to 4x cubed minus 18x squared plus 15x minus 20 for x equal to a half. So f for x equal to a half equal to 4 multiplying a half cube minus 18 multiplying a half square plus 15 multiplying a half minus 20 equal to 4 multiplying 1 per 8 minus 18 multiplying 1 per 4 plus 15 per 2 minus 20 equal to a half minus 9 per 2 plus 15 per 2 minus 20 equal to minus 33 per 2 equal to minus 16 a half. So the value of f(x) for x equal to a half its maximum return value, and maximum return point are a half point minus 16 a half. Step 4. Find the value of second derivative by using stationary point for x equal to 2 a half. Second derivative x equal to 24x minus 36 for x equal to 2 a half. So, second derivative for x to a half equal to 24 multiplying 2 a half minus 36 equal to 60 minus 36 equal to 24. 4x cubed minus 18x squared plus 15x minus 20 for x equal to 2 a half. f x x or 2 1/2 equal to 4 multiplying 2 1/2 cube minus 18 multiplying 2 1/2 square plus 15 multiplying a half minus 20 equal to 4 multiplying 125 per 8 minus 18 multiplying 2 1/2 square plus 75 per 2 minus 20 equal to 125 per 2 minus 18 multiplying 5 per 2 square minus 75 per 40 per 2 equal to 125 per 2 minus 18 multiplying 5 per 2 square minus 35 per 2 equal to 125 minus 35 per 2 minus 18 multiplying 5 per 2 square equal to 160 per 2 minus 18 multiplying 25 per 4 equal to 80 minus 9 multiplying 25 per 2 equal to 18 minus 225 per 2 equal to 160 minus 225 per 2 equal to minus 65 per 2 equal to minus 32 and a half. So the value of fx for x minus for, for x equal to a half its minimum return value and minimum return point are 2 1/2 point minus 32 and a half.
Determine the value of velocity and acceleration. If the function is now y equal to fx, then the first derivative can be written y-action equal to f-action x. F-action x often also written dfx, dx, and y-action also written dy, dx. If now s equal to ft, then the first derivative of s be written ds dt equal to f action t. F action t is equal to lim h to 0 f of t plus h minus ft divided h. Ds dt is the instantaneous velocity for each moment, or written v equal to ds dt or a equal to dv dt. dv dt equal to d squared s dt squared, which dv dt is the magnitude of the acceleration at every time. To understand more about the value for velocity and acceleration, consider the following example. A particle moving in a horizontal line following the equation st equal to t cubed plus 3t squared plus 5 with a distance of unit in meters and seconds. Find the velocity and the acceleration at t equal to 3 seconds. The first, find the velocity at t equal to 3 seconds. So, all we have to do is just take some derivative of our function. St equal to t cubed plus 3 plus t squared plus 5. V is equal to ds dt equal to 3t squared plus 6t. Well, that means the velocity at 3 seconds, all we have to do is just it in 3t squared plus 60. So if we plus in 3, we will get 3 times 3 squared plus 6 times 3 equal 27 plus 18. So we will get 45 meters. So we will get the velocity is 45 meters per second. And then find the acceleration. Well, again, we know our velocity time is 3t squared plus 60. And the velocity or is equal to dv dt equal to 60 plus 6. So the acceleration at 3 seconds we have to do is just put it in 60 plus 6. So we will get 6 times 3 plus 6 equal to 18 plus 6, and then we get the acceleration is 24 meter per second squared.
Example 2. The distance traveled by a car in time t is given s equal to 1 per 4 t to the power of 4 mean 3 per 2 t to the power of 3 mean 6t squared plus 5t. The maximum speed of the car will be reached when t equal to seconds. Answer. Step 1. So we are asked to find the time when the car reaches its maximum speed. Remember the maximum velocity condition v action equal to 0, but the formula for the function v we don't know yet, so we have to find the formula v first. So v equal to s action. And then the derivative of 1 per 4 t to the power of 4 is t to the power of 3. Mean the derivative of 3 per 2 t to the power of 3 is 9 per 2 t squared. Mean the derivative of 6 t squared is 12 t plus the derivative of 5 t is 5. Well, so this is the equation of v, but because he stated the maximum speed, remember the maximum or minimum requirement is the first derivative which is equal to 0. So the maximum condition is v action equal to 0. Step 2. So we just need to derive the equation v. The derivative of t to the power of 3 is 3t squared. Mean the derivative of 9 per 2 t squared is 9t. Mean the derivative of 12t is 12 plus the derivative of 5 is 0, and then so this equal to 0. Okay, we like factoring to find the value of t, but because we can divide it by 3, then we divide it by 3 first. And then we get t squared mean 3t mean 4 equal to 0. We like factor, we get t mean 4, t plus 1 equal to 0. From here, we can value t equal to 4 or t equal to mean 1. And then, okay, we already have a value for t, but since t is time and time cannot be negative, then t equal to mean 1 does not fulfill, so the time required is 4 seconds.
Mathematical models relate to extreme values of function. Before we begin, we'd first like to differentiate between local extrema and absolute extrema. This is best accomplished by means of an example. Consider, if you will, the graphs of three polynomial functions in figure 1. This is figure 1. Definition of absolute maximum. Suppose that C is in the domain of a function f and fc more than or equals to fx for all x in the domain of f. Then we say that fc is an absolute maximum of the function f. Similarly, if fc less than or equals to fx for all x in the domain of f, then fc is an absolute minimum of the function f. Definition of local maximum. Let C be in the domain of f if fc more than or equals to fx for all x in a neighborhood containing C. Then we say that fc is a local maximum of the function f. On the other hand, if fc less than or equals to fx for all x in a neighborhood containing C, then we say that fc is a local minimum of the function f.
Example: the sum of two numbers is equal to 5. Find two numbers whose sum is 5 and the sum of their square must be a maximum. Answer: Step 1. Choose x as first number and y as second number. So, x plus y is equal to 5. Step 2. Find the constraint that relate to two variables to one another. Y is equal to 5 minus x. Step 3. Maximize the sum of the squares, which means we have to define an equation that represents the sum of the squares. S is equal to x squared plus y squared. S is equal to x squared plus 5 minus x squared. S is equal to x squared plus 25 minus 10x plus x squared. S is equal to 2x squared minus 10x and 25. Find the derivative of this variable. S is equal to 2x squared minus 10x plus 25. S derivative is equal to 4x minus 10. Step 4. Set the derivative to 0 and solve for x and y. 0 is equal to 4x minus 10. 4x is equal to 10. X is equal to 5 per 2. Y is equal to 5 minus x. Y is equal to 5 minus 5 per 2. And then y is equal to 5 per 2. Step 5. We need to find the sum of their square to get maximum. X squared plus y squared is equal to 5 per 2 squared plus 5 per 2 squared is equal to 25 per 4 plus 25 per 4 is equal to 50 per 4. So the sum of their square is 50 per 4.
Example application. A square piece of cardboard measures 24 inches per side. John cuts 4 smaller squares from each corner of the cardboard. Tossing the material aside, he then bends up the sides of the remaining cardboard to form an open box with no top. Find the dimension of the square cut from each corner of original piece of cardboard so that John maximizes the resulting volume of the box. Answer. This is the models of the question. Step 1. Suppose the length of square cut out of the corners is x as shown in the picture. Step 2. Because each side of the original square measured 24 inches and we are cutting two lengths of 8 inches of each end. The resulting length is 24 minus 2 8 inches and width is 24 minus 2x inches and the height is 8 inches. Step 3. Because the volume of a box is computed by taking the product of the length and width of the base multiplied by the height of the box, the volume of the box is given by the formula. Vx equal to 24 minus 2x multiplied by 24 minus 2x multiplied by x equals to 576x minus 96x squared plus 4x cubed. Step 4. Set v action x equals to 0 to get maximum value. Vx equal to 576x minus 96x squared plus 4x cubed. V action x equals to 576 minus 192x plus 12x squared. And then V action x we change with 0. So 0 equals to 12 multiplied by 48 minus 16x plus x squared. So begin factoring the equation on the parentheses. So we get 0 equal to 12 multiplied by 4 minus 8 multiplied by 12 minus x. So x1 equal to 4 or x2 equal to 12. To determine the type of the stationary value, use the signs of v action x. So we get the value positive and then negative and then positive. It seems that Vx reaches maximum at x equals to 4, so the length of the side must be cut to get maximum volume is 4 and the volume is V equals to 576 multiplied by 4 minus 96 multiplied by 4 square plus 4 multiplied by 4 cube equals to 2304 minus 1536 plus 256 equals to 1024 inch cube. So, the resulting maximum volume of the box is 1024 inch cube. Thank you.